Hello, grade 6 math students. This is chapter 4.1, Ratio, Comparing Two Quantities. There are three main ideas in this chapter. The first is to write ratios to compare two quantities. The second is to interpret ratios given in fraction form. And the third is to use a ratio to find what fraction one quantity is of another, or how many times as great one quantity is as the other. Let's get started. Let's begin by simply building an understanding of what ratio is. You can compare numbers or quantities by comparing their sizes. For example, looking at our picture below, we have 7 orange cubes and 4 green cubes. There are several different ways we could compare these numbers. We could say 7 is greater than 4, or we could say 4 is less than 7. When you write a ratio, all you're doing is comparing numbers or quantities. The numbers or quantities you're comparing are called the terms of the ratio. So if we were to write a ratio of orange blocks to green blocks, we'd use these two terms, 7 and 4. Suppose there are 7 bags, though, of orange cubes and 4 bags of green cubes. If each bag has an equal number of cubes, then the ratio would actually stay the same. So the ratio of cubes themselves would be 7 to 4. We use this colon between the two numbers to communicate the ratio. But the bags could also be 7 to 4. The ratio itself does not have to be the actual number of cubes. It just has to explain the relationship to us. All it's telling us is that for every 4 green cubes, there are 7 orange cubes. When two quantities, such as the length of two lines, have the same units, they can also be compared using a ratio without the units to compare the quantities. For example, let's say this line is 5 centimeters and this line is 9 centimeters. 5 centimeters and 9 centimeters have the same unit. So the ratio of the top line to the bottom line could be written as 5 centimeters to 9 centimeters. But we can leave off the units because they're the same. We could simply write this as 5 to 9. If you want to use a ratio to compare two quantities that have different units, such as meters and centimeters, or feet and inches, you must first express the quantities using the same unit. Let me show you an example. Let's say we want to compare 3 centimeters to 4 meters. They have different units, so we cannot write a ratio for these. However, we could express 4 meters as 400 centimeters. Now, since both quantities are in the same units, we can write a ratio. So this would be 3 to 400. Remember, you cannot compare two quantities using a ratio if they cannot be expressed using the same unit. For example, you could not compare 3 centimeters, a length, to 4 kilograms, a weight, because they cannot be expressed in the same unit. Let's try a few sample problems on your own. There are 2 problems to try on this page, and there will be following screens. So please press pause, complete these problems in your notebook, and come back when you're ready for number 3. Here's screen 2 of your practice problems. Complete number 3, 4, 5, and 6. And then there will be one more page with problems 7 through 9. Complete these in your homework notebook. Press pause while you do that and come back when you're ready for number 7. Here are your last 3 practice problems. Each of these problems asks you to convert the units. For example, in number 7, you have 13 centimeters in a ratio to 2 meters. You know you can't compare those because they don't have the same units. So next to the problem here, it gives you a clue. It says think about 1 meter being equal to 100 centimeters. So 2 meters would be equal to how many centimeters? Fill that in and complete your ratio. You'll do the same for number 8, 5 kilograms to 13 grams. Again, there's a key over here for you to tell you how many grams, are in a kilogram. And then finally for number 9, you have 9 milliliters to 7 liters. So you have your clue over here that tells you how many milliliters are in a liter. Go ahead and complete these problems and come back to do some more ratios with me. Now that you've mastered writing simple ratios, we're going to use part-part or part-whole models to show ratios. This is another way that we're using these bar models that we've learned about for the last few years. So let's start with a simple problem. There were 55 adults and 32 children at a party. We want to find the ratio of the number of adults to the number of children at the party. And we're going to use a part-part model to do that. So we'll begin by drawing one long bar that we're going to divide into 55 and 32. So this is called a part-part model. So the ratio of the number of adults to the number of children at the party would be, well, all we have to do is put our colon in right here, 55 to 32. Now let's find the ratio of the number of children to the total number of people at the party. This will use a part-whole model. Our part-whole model actually begins with our part-part model that we've used here, 55 and 32. All we're going to add is our indicator for the whole. The whole will be valued as the total number of adults and children, so 55 plus 32, or 87 people. So now we want to write a ratio of the number of children to the total number of people. So our new ratio will be stated as 32 to 87. We'll close out part 1 of chapter 4.1 with 3 sample problems in which you will draw part-part or part-whole models to determine ratios. Number 10 asks you to find ratios of angelfish to guppies in John's aquarium. When you finish this problem, come back and I'll show you number 11. And here are your final 2 problems for chapter 4.1 part 1. Please go ahead and use the part-part or part-whole models to calculate these ratios. Put your answers in your homework notebook, and when I see you tomorrow, we'll practice some more ratio problems, as well as move on to writing and interpreting ratios as fractions. Have a great night, and I'll see you tomorrow.